All right, so we're going to move into the second half of Unit 8, which is going to deal with 8.5 through 8.9. We're going to wrap up evolution, and we'll start with 8.5, which deals with natural selection types. So with anything that data is collected, it's going to have to be measured, and the evolution and data for evolution is no different, and that data has to be measured. So how do we measure it? So evolution is typically tracked by measuring allele frequencies within a population, and evolution can also be measured by simply tracking the occurrence of a particular characteristic in a population over time. And typically these can be put on, as it says here, a scatter plot, but normally you'll see them in like a bell-shaped curve bell-shaped graph, and we can use that bell-shaped curve to decipher what is exactly happening within that population, what type of evolution is occurring. So with standard selection, the two extreme conditions which are going to be at either end, and what we mean by end is either end of the graph or the line, will have less representatives than the one in the middle or the intermediate condition. This serves as a starting point for measuring natural selection, and natural selection can affect the distribution of physical characteristics or phenotypes in three ways. So extreme condition, and then the intermediate or the middle, I'm sorry, I'm having a problem speaking, middle characteristic here at the top of the bell curve. Okay, so in this particular, the standard graph, the middle characteristic is favored and the extreme conditions are being selected against. Stabilizing selection. So this is when the intermediate condition is selected for or services and reproduces in its survives and reproduces in its environment. So the extreme conditions are selected against, and they have a much smaller chance of survival or being passed on to the next generation. So in the graph down here at the bottom, the ends of the bell curve are going to be pulled towards the middle, and the middle is going to increase. Okay, so the length or the overall size of the bell curve is going to get smaller as it looks like just one big hill or mountain or hump. You have directional selection. This is when one extreme is selected for and the other extreme is selected against. So in this particular situation, the graph is basically going to move either to the right or to the left. What we mean by move is the middle point is going to push one way or the other towards an extreme condition. So in the picture here, with the standard graph, you'll see here it's supposed to be in the middle, but we've noticed that it's being pushed towards the right, meaning that this particular trait is being selected for, and this particular trait is being selected against, and the middle or intermediate trait is beginning to see a decrease in the amount available. And then you have disruptive selection, and with disruptive selection we see that both of the extreme conditions are selected for while the intermediate or the middle condition is being selected against. And this is basically a reverse bell curve if you want to look at it that way. All right, so is natural selection random or non-random? So natural selection is non-random because the organisms best adapted is the most fit within that population. There are random events that can happen to a population that do not take an organism's fitness into account. So we're talking about some things that can happen that can cause natural selection or evolution that does not take an organism's fitness level into account when making the decision of what's going to happen. First one is gene flow. So this is when organisms are going to leave the gene pool or enter the gene pool. This can cause a drastic change in the population because of new alleles or new traits being introduced or removed from that gene pool. So over time, we could see evolution begin to occur based off the alleles that are within that population to be reproduced and passed on. Of course, mutations are technically random. They weren't on purpose, and they can cause changes in individuals, which could have an effect on the population. So if a mutation occurs, and that mutation, of course, is not detrimental or life-threatening, and it is able to be sustained, and it is continually sustained generation after generation, then it can lead to evolution. Genetic drift, so random changes in a small population's gene pool. Okay, so for whatever reason, let's say that there's an individual that has two different colored beetles in his house, and that is this population is the beetles' environment, and the individual really likes to squish the green beetles, but not the brown beetles. So over time, as the individual smushes the green beetles, the brown beetles are going to thrive even though they're part of the same population, just different color, let's say, shells over their top side. So it's just a random change there in that particular population. That's going to change the overall population's gene pool. Less green beetles to pass on the green beetle color because they're being smushed. All right, so genetic drift, you see bottlenecking. So drastic reduction in a population due to a natural occurrence. So with this, we're talking about volcanoes, floods, fires, anything along those lines. So with these events, an organism's fitness level is not a factor, meaning that whether you survive or die, these particular natural events doesn't relate to your fitness level. It's just, are you lucky or not? Okay. When a forest fire comes through a forest, it doesn't care which bear has the highest fitness level. If that bear doesn't get out of the way, the strong bear will die just as quickly as the weak bear, so on and so forth, if you get to understand what I'm saying. So the organism's ability to survive long enough to reproduce does not matter in bottlenecking events. So another type of genetic drift, you have the founder effect. This is when a small group of a population moves away, taking a smaller gene pool with it. So the smaller gene pool will increase as the population does, which will make the allele frequency in the new population different from the old one. And that is the end of 8.5. So there is a form that goes with this. If you have questions, please let me know. Thank you.